Okay, guys, so we are going to continue with chapter number 2 and try to finish it quickly so we can move on to the lab. I have posted the homework set last week, which is going to be due next week when we will finish, of course, this chapter today. So you will be able to do all the problems. Although I think I told you that you should be able to do quite a few problems from last week. If you have done those problems, then there will be like 4 or 5 problems left for this week. And of course, then there's going to be quiz from this chapter next week once you submit your homework. And I think we are doing another lab next week as well. So it's going to be a busy day next week. Although the chapter number 3 is a short chapter, so hopefully we should be able to finish everything. So let's go ahead and continue. We left off with the discussion of voltage controlled current sources. We discussed 3 voltage controlled current sources. Anybody wants to tell me what is the main idea behind a voltage controlled current source? What is the characteristic of a voltage controlled current source? Yeah, very good. So the load current does not depend on the load itself, and it is controlled by the input voltage, irrespective of what load is connected. It's not going to change. Current controlled voltage source is a voltage source. It's producing a voltage. The output voltage of a current controlled voltage source should be proportional to the input current and must be independent of the load resistor. So similar to the voltage controlled current source, the current controlled voltage source, the voltage of the current source is going to be independent of the load, and it is only going to depend on the input voltage. So one of the circuits is in front of you, and this circuit, you can assume this circuit to be an inverting amplifier if the current that is coming is the input current. The voltage source is not shown, the current is shown, so current can be coming from any other circuit, but it is entering in the inverting input of the operational amplifier. And of course, this is going to be virtual ground. So the output voltage right here, since the current is going to come here and it's going to flow through resistor R, so this is going to be the same current, I input. So the output voltage will simply be 0, or this current I input will be 0 minus V out over R. And output voltage will simply be negative I input times R using Ohm's law, which you see this equation right here. In this case, we call R to be the trans resistance of the circuit, generally denoted by Rm. And any resistor connected between the output node and ground. So if you connect any load resistor over here, it's not going to be affected by the output voltage, and it will be dependent on the input current source and the trans resistance, which is the feedback resistance. Because the output voltage, you do not have any RL in the output voltage equation. Output voltage is simply be dependent on the feedback resistor or trans resistance, on what we are calling. So in this case, this circuit can be considered as a circuit that the output voltage is only dependent on the input current, but independent on the load resistor. So this can be considered as a current controlled voltage source. Then we have current controlled current source. That is, your output current of the current controlled current source is proportional to the input current and independent of the resistors that is connected as a load. So this is one of the circuits. You have R1 here. This is R1. you have R2 here, and you have the load resistor right over here. R1 and R2 are connected between node A and ground, because this is virtual ground and this is node A. So R1 is connected between node A and the actual ground, and R2 is connected between node A and virtual ground. So in any case, both are connected between node A and ground. Hence, both R1 and R2 are going to appear to be parallel to each other because they're connected between the same nodes. One is connected at the actual ground, one is connected at the virtual ground, but the voltage of virtual ground or the actual ground, both are considered to be 0. So these two resistors, although they don't appear to be parallel to each other, but in this circuit, they will act as parallel to each other. They may not appear to be parallel, but they will act as parallel to each other. So whatever the voltage across R1, the same voltage is going to appear across R2, and we are assuming that voltage to be V2. V2 is simply I1 times R2. That's your V2. I input times R2. So the same voltage is going to appear across R1 as you see right here. I1 is coming from the ground to node A, ground to node A. So the load current, this load current is a combination of these two currents right here, I input and I1. So if you apply KCL at node A, I load is equal to I input, which is this current, and I1, which is current passing through R1. I input plus V2 over R1. I1 is V2 over R1 using Ohm's law. And V2 is I input times R2. So I'm going to go ahead and replace this V2 by I input times R2. And then I'm going to write this equation down in terms of I input and the load current. So load current is equal to I input times 1 plus R2 over R1. So you can see that the load current is independent of the load value itself, which is RL, and only dependent on the values of R2 and R1, which we're calling this factor to be beta. So load current is equal to beta times I input, and beta is independent of the load resistance. So that equation 2.14, again, it shows that load current is directly proportional to the input current and it is independent of the load resistor. And again, that's the purpose of the current controlled current source, that any current that is passing through the load resistor should be independent of the load resistor and only depends on the input current. Load current depends on the input current. Let's determine dynamic range of the input current, like we did last week, dynamic range of the load current. So dynamic range of the input current to determine dynamic range of the load current. We can apply Ohm's law across the load resistor, this resistor. We have VA minus V out over RL, which will be equal to IL. So VA minus V out over RL, which is equal to IL. And VA, this node voltage VA, is equal to negative of V2, because V2 is from 0 to, of course, node VA. So VA will be equal to V2 is equal to 0 minus VA. So VA will be equal to negative of V2. And that's what we do over here. Replace VA by negative V2 minus V out over RL, and V2 is I input times R2. V2 is I input times R2. I'm gonna go ahead and put that. And then write this in terms of V out. So V out is equal to I1 times R2 plus IL times RL, or minus IL times RL. Multiply both sides by -1. And then we have, let's see. Okay, right here. So negative I1, set I input, negative I input times R2, and negative I input times 1 plus R2 over R1, which is my load current right here. 1 plus R2 over R1 times I input. So we go ahead and plug that value in. And then simplify this in terms of the input current. Oops. And after simplification, we are going to find out what will be the dynamic range of the input current in order for the output voltage to be less than V saturation. And then we can relate that, the dynamic range of the input current to the dynamic range of the output current, because output current, or load current, sorry, load current is equal to input current times beta. Beta is 1 plus R2 over R1. So dynamic range is important in the sense that if you exceed that, your circuit is not going to work as the current controlled current source or voltage controlled current source, and so on and so forth, because your circuit is going to go in the saturation mode. All right, let's look at one of the examples. A current controlled current source as shown, and yes, go ahead. Instead of less, you're saying? Well, we already have the I1 less than VSAT over there. That's why we put it. Yeah, so base is based on that. So it's going to be less than VSAT when we are using that. And that is related to the load current. So it's automatically be less than that value, basically. A current controlled current source shown in figure 2.14, which is this figure right here. R2 1K, input current is 1 milliampere, gain of the current source is 50. Determine R1 load current, maximum value of the load. So let's go ahead and draw the circuit first. Negative, positive, negative, positive. Okay. So this is my input current right here. I input, my V2, I input, and this is R2, this is R1, I1, node A, RL, and VR. So this is my circuit. R2 is 1 kilo ohm, this resistor. Input current is 1 milliampere. So this current is, 1 milliampere. And R2 is 1K. This is 1K. Resistor. We don't know the value of R1. We can find the value of R1 since beta is given to us. This is the value of beta that is given to us, current gain. Since the load current is 1 plus R2 over R1 times the input current. Load current is I1 times R1, 1 plus R2 over R1. And this quantity is your beta, which is given as 50. R2 is given as 1K, and we have to find R1. So go ahead and see what is the value of R1. 49, 1000 over 49. 20.4 ohms. So this R1 is going to be 20.4 ohms. Calculate the value of load current. IL is equal to beta times I input. I input is 1 milliampere. Beta is 50. So 50 times 1 milliampere is 50 milliampere. This is part 1. Part 2. Load current is going to be 50 milliampere. What will be the maximum value of the load resistance in order to produce a linear operation if our saturation voltage is 13 volt? So dynamic range we are looking for. Go back to the slide. We know the I input value, we know R2, we know R1. We have to figure out RL if this product is less than V saturation. Let's go back. I input times R2 plus beta times RL. Remember, this thing is beta right here. This is beta. 1 plus R2 over R. So from this, I input, so we can write this down. This should be so for the equality case. Well, we can find out R2 beta RL for the equality case, V saturation over I input minus R2. So RL divided by beta. All right, go ahead and calculate that. So this is the maximum value of RL that is allowed before it will hit saturation. Any value that will exceed this, the one that you're calculating, is going to make this product higher than V saturation. So V saturation is 13, I input is 1 milliamp, so that's 13K, 13K minus R2, which is 1K, 12K, 12K over 50. So 12,000 over 50. How much? 240 ohms. Okay. So this is the maximum value of RL that you can use for the dynamic range. Any value that exceeds this, the circuit is not going to operate as the current controlled current source. Is not going. All right, guys, question about this? Any questions? I believe this concludes the discussion of dependent sources. So we looked at 3 different type of dependent sources: voltage controlled current, current controlled current, and current controlled voltage sources. The last couple of circuits that are left, that are very important circuit, actually linear combination circuit, we were discussing in DSP as well when we were discussing ADC and DAC. Linear combination circuit or summing amplifier, as you can see, it is a type of inverting amplifier. However, the inverting input is connected to multiple sources, and each source has some sort of input resistance or a resistance connected between the inverting input and that source. And the idea of linear combination circuit or summing amplifier is that all the voltages that are coming in that are connected to the inverting input, those voltages are going to be added together, multiplied by their individual gains, and reflected at the output. So basically, it adds up all the voltages or all the sources that are connected at the input and reflect that at the output multiplied by their respective gain. That's the idea of the combination circuit or summing amplifier. So as you can see, this is dot, dot, dot. As you can see, output voltage for a summing amplifier is equal to gain of the first source, A1 times V1, plus gain of the second source, plus gain of the third source, all the way up to gain of the nth source. When we do the derivation for that equation, apply KCL at the virtual ground. This is virtual ground. Apply KCL at virtual ground. Then the feedback current will be equal to the current of each individual branch that is connected to the virtual ground. So the feedback current will be equal to I1 plus I2 plus I3 all the way up to IN. And applying Ohm's law on each of the branch, we can write down the expression for the current in terms of voltage and the resistor. So V1 minus 0 over R1, V2 minus 0 over R2, so on and so forth. V1 over R1, V2 over R2, all the way up to Vn over Rn. And that will be equal to current IF, which will be 0 minus V out over RF. So minus V out over RF. Therefore, V out will be equal to negative of V1 times RF over R1 minus V2 times RF over R2 minus V3 times RF over R3 and so on and so forth. Negative RF over R1 V1, RF over R2 and so on and so forth. So output voltage will be equal to negative of A1 V1 plus A2 V2 all the way up to AN Vn. And of course, negative sign is there because this is an inverting amplifier. Your inputs are connected to the inverting input of your circuit, not the non-inverting input. If you want to convert this such that the output and input are in phase, what you're going to do? What can you do? Yeah, but this circuit, let's say you have this circuit, and then you want the output to be in phase with the input. What you can do? You can say it again. Put another inverting amplifier after the output with a gain of 1, right? Put another inverting amplifier after the output with a gain of 1, and that's going to change the phase. So it's going to become positive, and it's going to become that equation. V out is equal to A1 V1 A2 V2. So that's what we're going to do, right? And that's what you see over here. Basically, you have the inverting amplifier, the summing amplifier, and then you put another inverting amplifier here with the same value of the feedback resistor and the input resistor, such that the gain is going to be 1 RF over R1, and it is going to just invert the phase, and the output will be simply the combination of the input times the respective gain. In this case, since all of these resistors are 1, feedback resistor is 10, then the gain of each branch is simply going to be 10 over 1. So gain of each branch is going to be 10. So when you have your expression of the voltage over here, let's say this is V out 1. V out 1 will simply be negative 10 times V1 plus V2 plus V3, because gain of each branch is simply 10K over 1K. And then that passes through the second stage of inverting amplifier, which has the gain of 1, and this is going to invert it back, and it's going to be simply 10 times V1 plus V2 plus V3. So the gain of this whole combination is simply 10. Each input is multiplied by 10, added together to produce the output. Make sense? Give me 1 second. Two tone signals with frequencies 1 kHz and 5 kHz are added together to produce a compound signal with 2 frequencies as shown below. So one signal has a frequency of 1 kHz sine 2000 pi t, and the other signal has a frequency of 5 kHz sine 10,000 pi t. What we want is to create a circuit with an output of 5V1 minus 2V2. That is 5 sine 2000 pi t minus 2 sine 10,000 pi t. So we have to design a summing amplifier for that. A couple of ways to do that. So we know that summing amplifier produce a negative output. right? And to make it positive, of course, we have to invert. We can invert the signal after the summing amplifier. Now, in this case, our V1 is positive, our V2 is negative, right? So one way to do this is you have an inverting amplifier. You put an inverting amplifier with a gain of 5 and input V1. So let's say this is my V1. I want a gain of 5. To gain of 5, you can choose, let's say 10K and 2K. So my RF1 is 10K and my R1 is, let's say, 2K. That gives me the output V out1 to be equal to what? Negative 5V. And now if I apply a summing amplifier with one of this input going as one of the input and the other input as my V2 times gain of 2, then the output of that is going to be negative of this, which will be 5V1, and negative of the other input, which is going to be negative 2V2. So if I have now a summing amplifier, this is my V2. And whatever, I can put a resistor here as well instead of shorting it out. Whatever this resistance is, the same resistance is going to be this value, but I need a 2 gain of 2 with V2. So let's say if I choose this to be 4K, this to be 2K, so I will just choose this to be 4K as well, right? So let's say this is my R2, this is my R3, and this is my RF. And this is the output. So in this case, my output will be equal to negative of, let's do this first, RF over R3 times V out 1 plus RF over R2 times V2, which will give me negative of RF over R3 is going to be, of course, 1, and V out 1 is negative 5V1. And RF over R2 is going to give me 2, and V2 is, of course, V2, which will give me 5V1 minus 2V2. And that will give us our circuit. Now, there's one way to do it, of course. You can have multiple ways, multiple combinations that you can employ. But this is just one way, easier way, perhaps. Make sure not to do one thing. Sometimes I give a problem like this, and what students do is they put a summing amplifier. So they do this usually. Summing amplifier, negative, positive. V1 and negative V1 and V2. R1, R2. That's what they do. So don't do that. It's not, it's not negative V. Negative means that you're changing phase, right? So show that you're changing phase by putting first an inverting amplifier like this. So the output of this is going to be negative V1. In this case, I also use the gain of 5. If you don't want to use the gain of 5, that's okay. You can just put the gain of 1 and have negative V1, but that's going to go here in that case, right? But do not show just, oh, my input is negative V1. No, negative V1 is not an input. If you're connecting your function generator with your circuit, it's just going to be V1 or V2 or V3, whatever input is that. Negative V1 or whatever phase difference that you're creating, you have to create that phase difference, and that requires another circuit, right? So make sure anytime you are doing linear combination circuit, and if one of the input is negative, other are positive or whatever, make sure do not show the input itself as negative. It's just the input variable is V1, V2, V3. Those are our input. It's not negative V1. Yes, Diego? Negative is because this is the linear combination circuit is an inverting amplifier, right? RF over R3 is going to be 1, right? And then V out 1 is negative 5V1. Yeah. Yes. Yeah, I'm just showing you the expression, and then I'm putting the values. That's about it. Yeah. I'm just showing the expression. Yeah, you don't really have to show me that. Once, if I ask you to design the circuit, then that's the circuit design. Even if you don't write the expression, that's the circuit design. You get full points if you do a correct design. You don't have to show me the expression for the circuit design. Yeah. Mm-hmm. So once again, do not do this. Don't do this. Let me write it down. In case. Yeah, don't take input as a negative itself. Input is just variable, V1, V2, V3, V4. And those are signals. All right, so I'll delete this slide since we already draw the circuit. Okay, last circuit of this chapter. So we discussed the linear combination circuit or summing amplifier. Now we're going to look at the closed loop differential amplifier. Now remember, operational amplifier itself is a differential amplifier, right? It takes the difference of the input voltages between the inverting, the non-inverting input and inverting input, multiply that by gain A, and produces that output. But we do not use the circuit in the open loop configuration because again, A is extremely large and any small voltage at the input is going to push the output into saturation. So we use the circuit in the closed loop configuration so that we can set our own gain. And this is one of the circuits that we can create that is going to take the difference of the two inputs connected at your inverting input and non-inverting input and multiply that by a gain and produces the output. So closed loop differential amplifier amplifies the differences of voltage applied to non-inverting and inverting inputs of an amplifier. Gain of each of this input can be set differently, or we can also set one gain for the whole circuit. So A times V1 minus V2 or A1 V1 minus A2 V2. You can have output either A times V1 minus V2 or V out is equal to A1 V1 minus A2 V2. Both outputs are possible. So how does this circuit work? We apply voltage division right here to find out what is V positive. Voltage at the non-inverting input. using voltage division, that's going to be R2 times V1 divided by R1 plus R2. R2 times V1 divided by R1 plus R2. And again, remember, we can apply this because we do not have any current that goes in here. So the current that is coming from V1 is just going to go through R1 and it's going to go through R2 and ground. If the current goes here, then you cannot apply voltage division because then they will not appear in series. Remember that, right? But right now they appear as in series because no current flows inside the operational amplifier. So the current coming R1 is going to go through R2 and ground. And therefore we apply the voltage division. So this will be the voltage at the non-inverting input of the operational amplifier. The same input is going to appear at the inverting input, V negative, because of V positive is equal to V negative that we've been using. So voltage here is going to be the same, R2 over R1 plus R2 times V1. We show this current to be I3, this current to be I4. Of course, I3 will be equal to I4. So I3 will be equal to I4. V2 minus V positive over R3, V2 minus V positive. So V positive and V negative are the same, of course, is equal to V positive. V2 minus V positive over R3 is equal to V positive minus V out over R4. V positive minus V out over R4. And of course, V out over R4 is equal to, we take this V positive over R4 on the other side of the equation. So we have 2 V positive over R4 plus V positive over R3 minus V2 over R3. All right, and let's see, what did we do? We were just manipulating the equation. And V positive is here, 1 plus R4 over R1 minus R2 V4. So again, manipulation of the equation. And finally, we went ahead and we wrote down what V positive is. V positive is V1 times R2 over R1 plus R2. So V1 times R2 over R1 plus R2. That's our V1. Oh, not this whole thing, V1, sorry, V positive. This is our V positive. V1 times R2 over R1 plus R2. Times R1 plus R4 over R3. This is 1 plus R4 over R3 minus R4 over R3 V2. So this can be considered as one of the gains, A1. And of course, R4 over R3 can be other gain, A2. So this is going to give you A times V1 minus, A1 times V1 minus A2 times V2. So the difference of both input voltages multiplied by their respective gains is the output. If you want A1 and A2 to be the same, that is one gain multiplied by V1 minus V2 to produce the output, then you have to do this. You have to take R1 to be equal to some resistor R and R2 to be equal to some resistor A, R1, whatever gain you are setting. R3 will be equal to R and R4 to be equal to A times R3. There are 4 resistors in the circuit. If R1 and R3 are set to R, R1 and R3, if they are set to value R, and R2 and R4 are set to value A times R, then once you go ahead and plug these in this equation, you are going to get A1 and A2 to be the same value, which we can consider as the gain A. Therefore, the output will be equal to A times V1 minus V2. And that is called a balanced differential amplifier. That is, the gain of each input is the same. When it is the same, it is called balanced differential amplifier. All right, guys, question? No questions? Everything is good? So what did we do in this chapter then? We started with, of course, general discussion of operational amplifier. We looked at the circuit, which is a huge circuit, many transistors, resistors, and all those things. We discussed that what are the ideal conditions under which we use operational amplifier, which are input resistance is extremely large, output resistance of operational amplifier is extremely low, gain is almost infinity, open loop gain. Input current going into the positive terminal and negative terminal, it is considered to be 0 because of the extremely large input resistance of the operational amplifier. The positive terminal voltage, inverting terminal voltage, is equal to the non-inverting terminal voltage in any circuit. Those are all the ideal conditions, right? Then we discussed, based on the ideal condition, we discussed inverting amplifier first. That takes any input, multiply by the gain that you're setting, which was RF over R1. Invert the phase, change the phase by 180 degrees, and produces the output. So that's inverting amplifier, very commonly used amplifier. That's the one that you're going to do today in lab as well. Then we discussed non-inverting amplifier that does not change the phase of the output with respect to the input, and it has a gain of 1 plus RF over R1. We discussed voltage controlled current source, current controlled voltage source, and current controlled current source, multiple circuits. And then we discussed how to create a summing amplifier or linear combination circuit. Again, very commonly used circuit. As you saw, if you are taking DSP, we are using that circuit in the ADC circuit as well. And then this is the last circuit that we discussed, closed loop differential amplifier. So in the quiz, in the test, anytime you see word derivation, remember, do not put the formula or equation, final equation. Make sure you show the derivation with the current, current is going here, apply KCL and all those things. So make sure you do that. It might be very simple, but if you don't do that, then you're not going to get point if it is asked to do the derivation. If it is asked to do the design, like we did the design of the summing amplifier, then you'll have to show the design. You can choose your own resistor. Usually I give a range. Choose a resistor range between 1 kilo ohm to 10 kilo ohm, for example. So you can choose any resistor value per se if you're making a specific design. Because design, of course, you don't have any value. I mean, you can have your own value based upon what resistance are available and stuff like that. So design will still be valid as long as your output is in accordance with the required design, the requirement of the design. And the same thing goes for the closed loop differential amplifier. As long as you're choosing the resistor value for a specific gain, you can choose any resistor value within a range that is given to you. So with that, this chapter is finished. Let's go ahead and stop recording.